Okay, good morning. So as you can see, this is week 3, Tuesday. So today's agenda, we are going to go through eccentric. Okay, now it's different from last week. Last week was centric. We're going to look into eccentric unsymmetrical bending. Then we're going to deal with an example of location of neutral axis for unsymmetrical bending. And then we're going to start with one of the most confusing topic in structure analysis, which is shear stresses. Okay, it's confusing because there's a lot of rules to apply, but I have summarized the rules for you, so hopefully you will find easy. Then what I've done is I also have put in some I uploaded on Avenue. If you go into the Avenue, you'll see this page, and I hope you will download the images. And these are the image that we're going to use today for the lecture. Right. So now we're going to look at unsymmetrical, eccentric unsymmetrical bending. So a thing to observe is the structure is under axial load A, but this axial load has an offset, okay, which is at a distance PA or distance A from the y-axis, and a distance B. And what sort of distance? We are talking about perpendicular distance. Okay, so we are talking about perpendicular distance over here. So as we know, whenever we have a moment, or there's a moment whenever the force has a perpendicular distance from the centroids in either y or z axis. Okay, so I want you all to take note of this. So note that px, okay, px is not acting along or on the x-axis. Okay, so there's an offset of A and B. So from here we know that moment about y. Okay, so moment about y. So I'm going to change. So what we can see is moment about y will be equal to P in the x direction multiplied by A. Okay, so I'm addressing this as Px. So this will generate a moment in the y direction. So this is your My, right? So again, the head of the arrow is compression, the tail is tensile. Nothing changed to what we've applied so far. Okay, and then we will have moment about the z-axis. Okay, I'm going to change the color, the moment of z-axis is equal to Px multiplied by B. So we are going to generate a moment in this direction, right? So this is again our moment about Z. So our moment of Z over here on top is still under compression. Below the arrow is tensile. And then for the moment about Y is compression. And the tail end is tensile based on color. Okay. So our analysis did not change, right? So for this case, our bending stress will be equal to stress X is equal to Px divided by A. So the A over here defined, this is the A, which is the cross-sectional area. And then we have plus by My over Iyy multiplied by Z plus by Mz over Izz multiplied by Y, right? So this is the formula. It looks familiar, like the one that we have derived last week or shown last week. The only difference is what we have now is we have under eccentric loading, this is inducing an axial. Okay, this is due to axial loading. And both of these are my and z, this is due to bending moment. Bending moment loading. So this is the in eccentric loading, this is the only thing that changes. So nothing new at all. Analysis is exactly the same. Okay, the analysis that what we have to do is exactly the same. Nothing new, which is the beauty of what I'm teaching you. Okay, we just add on more vectors. That's about it. Right. Let's look at an example now. So far, anyone, any questions, please?
Eugene.
Yes.
Should one of those be IYY in the equation?
You got it. You got me. Your name.
Alyssa?
Yeah, you got it. Bang on. Thank you. One pint. Okay.
Thanks.
I get you a pint. I owe you guys a lot of pint. Right? When you will get your pint, it depends. Yeah, maybe I'll get your address. I'll send you pints back to your home. Okay. Right. Thank you so much. Okay. That's absolutely right. Right. So any other questions so far? Thank you so much. Are we good? No question? Right. So the next thing we're going to look into an example. Look at an example. So for this example, we're going to pick an example. Okay, as I said, you have these images on Avenue. You can copy them. Right. So what we have over here is we have a structure that has axial load. The axial load are at point E. So you can see we have point E, we have point H, and we have point G. We have axial load. So we want to find the stresses at point A. So we want to identify what is our stresses at point A. What's our stresses at point, for this question is point B. Okay, what are the stresses that are over there? So the first thing that we define is we have to define our axis. So I'm going to call this our Y. This is our Z. And lastly, this will be our X. Okay, so this is X, Y, and that's our Z-axis. Right. So for this case, we know that the structure is under unsymmetrical. Eccentric or eccentric unsymmetrical. Bending. Right. So we are aware that we have to use this formula, Px over A plus by My over Iyy multiplied by Z plus by Mz over Izz multiplied by Y. As I said before, don't worry about the what? Don't worry about the sign. Okay, don't worry. About the sign. We will worry about it later on when we do the analysis. Okay. Right. So the first thing we do, we're going to view this in the we're going to view this at the front. We're going to view it on the YZ plane. So I'm going to draw this on our YZ plane. And then the X is coming up and that's a rotation. Then we're going to sketch this out, the cross section. And then we will call this. So what we have over here, we have a force coming out at 150 pounds. we have another force coming out, 500 pounds. And then we have another force coming out. So I'm drawing dot. Dot means the arrow is coming towards you, right? So 250 pounds. And then we have our axis. So one of our axis, right? So these are our axis. So there's our y-axis. And this axis is in fact the location of our centroid. Okay, our centroid are on it also. Okay, so this is axis. So this is the first one is our YY. Then we have our ZZ. So first thing to take note, we are going to calculate what is our PX. So PX, all of them are acting away from the structure. So all of them will induce a tensile stress, right? So you have 150 plus by 500 plus by 250. So this will give us a 900 pounds force. And this 900 pounds force is going to be tensile. And then the next thing that we're going to look at is we're going to look at moment about y. Okay, let's do moment about y first. Okay, so we have moment about y. Now this is an assumption that I'm making. Okay, so if we have our thumb pointing upwards, this is your moment about y, and this is positive. So this is what I assume. Okay, that y is positive when my thumbs is pointing up using the right hand rule, and my moment y is positive, is going that direction. So from here we know that moment is equal to force multiplied by perpendicular distance So if we were to do moment about y, right? For this case, we're going to do moment. Let me copy this image again, then later on will be less confusing for you. So if we're going to do moment about y, right? So it's force multiplied by perpendicular distance. The critical thing is, what is this perpendicular distance? So everything is measured from the y-axis, right? Is measured from the y. So this is the distance that we should be considering, right? So this distance over here, I have to use a different color. So this is the distance that we're going to use now. So it's important to know what distance you're going to use. So we know this distance, they're all at 2 inches. Right? So we're going to calculate moment about y based on the assumption that clockwise or anti-clockwise, or this definition is positive. So my will be equal to 150 multiplied by 2 inches. So this is the 150 force, and it's positive because it's going to generate anti-clockwise rotation, plus by 500 multiplied by 2, then minus by 250 multiplied by 2. Okay, so getting the perpendicular distance right is critical. So this 300 plus by 1000 minus by 500. Right, so this will be equal to 800 pounds positive. So 800 pounds positive down here indicate that what we assume, right, that this is positive, right? So from here, we can immediately draw this out. So moment about y, right? So when moment about y is at that direction, we know that over here, this will be the head of the arrow induced by moment about y. This will be in compression, and the tail end of the arrow will be tensile. Okay. So we have been doing this for the past like 2 weeks already. And what is the beauty is this analysis, regardless of how the structure is loaded, the head of the arrow is compression, the tail is tensor, is a generic solution. Okay.